Greetings, everyone. Today we're going to talk about the difference between combined gas law and the ideal gas law. So previously, the combined gas law had some sort of change. It had initial pressure, it had initial volume, initial temperature, and whether we were solving for the ending pressure or the beginning, there was a change in one of those three aspects. However, when talking about the ideal gas law, we're not really concerned if there's a change or not, but there's a couple more letters that we're going to incorporate. So we already have P for pressure, we already have V for volume, we already have T for temperature. Can anybody remember what unit temperature has to be in? Definitely has to be in kelvins. And then there's the last two are the letters N and the letters R. So without further ado, let's see what's behind door number one. All right, so P is for pressure. Now, pressure can be in torr, millimeters of mercury, atmospheres, or kilopascals. But what we're really going to focus on the two units that are most very popular are atoms and kilopascals. So P, we're going to keep in the units atoms or kPa. Now volume, I wonder what unit volume has to be in. It has to be in liters, okay? Has to be in liters. Now, before, on the combined gas law, as long as the volumes were in the same units, everything was fine. It could have been in milliliters and milliliters. It could have been in liters and liters. However, for the ideal gas law, it's pretty finicky. It has to be in liters because we have these two additional variables and all of the units have to align. All right, now if we take away T, we know that T is definitely going to be temperature in kelvins. Okay, now the last two, N. N stands for the number of moles, So now we're incorporating number of moles of a particular molecule of gases, okay? Let's switch things up here. Let's go crazy. And let's draw a line. There you go. All right, and then the last one is going to be our gas constant. The R stands for a scientist named Raoult. So, but we're going to abbreviate by R. Now, R has two numbers. It actually has a couple more, but since we're only focusing on atmosphere or kPa for our pressure in units, we're going to only have two numbers to pick from. When it's in atmospheres, we're going to pick 0.0821. 0.0821. When our units for pressure are in kPa, then we're going to pick the 8.31. Okay, so reminder, when it's in atmospheres, we're going to use 0.0821. When it's in kPa, when our pressure is in kPa, we're going to use 8.31. Before we do some problems, let's review what we mean by ideal gas. Now, this is a make-believe gas. It's essentially a gas molecule that is the perfect gas molecule that could ever happen, that ever could be created, because of the fact that they form elastic collisions. Think of like two pool table balls ricocheting off of each other. There's no bonding because the fact that we're talking about gases means that they have to remain in the gas phase. They can't be liquids and solids because otherwise the formulas are going to go into some other type of formula. And we can't use our gas law formulas. There's no KE lost. There is no kinetic energy lost. Okay, so once they ricochet off each other, it's like they never had any impact in the first place. And remember, motion is random and it occurs very, 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 very fast. So that being said, we have some conditions in which help create a real gas, and if we put a real gas in these perfect conditions, we can simulate our ideal gas. So again, how do we make something that is very, 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 very fast? How do we speed up a gas molecule? Its temperature has to go up. How do we get these molecules to stop bonding and forming different molecules and losing their kinetic energy in the process? We make the playground or the volume very, very, very big. Big volume, big temperature. Hopefully these things don't interact very much. Additionally, when you make the playground very, very big for these gas particles, they are not going to be bouncing off the walls as frequently, so they are not pressing as frequently off these walls. Therefore, the pressing frequency or the pressure goes down. Pressure goes down. And then lastly, how do we help give it that last little bit of oomph to make it a very, very, very fast molecule? Remember, molecules with a low molecular mass are very, very fast. Molecules that are a little bit larger, a little bit slower. It's just the way the cookie crumbles. Now, let's do some practice problems here. Let me zoom in. Now, we're going to do the first couple of problems that are on your homework or your assignment in Canvas. Okay, so let me see if I can write this at the very top. Remember, we have our formula is PV equals nRT. I'm going to put a little Kelvin symbol next to the T just to help you remind. And then remember, R can either be 0.0821, or if it's in for atmosphere, and then if it's in kilopascals, oops, sorry, it's going to be 8.31 for kPa. Now, R can change based upon the different units for pressure, but again, atmospheres and kPa are the most most used, so we're going to stick with those two. All right, let's start with the first problem. If I have 4 moles, so we have 4 moles of a gas at a pressure of 5.68 TMs in a volume of 12 liters, what is the temperature? As you can see, we didn't have some starting, we didn't have an ending, there was no change. It's more like taking a snapshot of the picture. So let's start putting it in our formula. We have 4 moles. So 4 is going to be on the right-hand side because that stands for number of moles. And don't forget your units there, people. R, since it's atmospheres, we're going to be using 0.0821, 0.0821. And what is the temperature? So we are looking for temperature. Pressure is going to be on the left-hand side, 5.6 atmospheres. And then volume is going to be 12 liters. All right, now we have an equal sign. We have numbers on either side of the equal sign. Just know that if you have a number and you want to get it to the other side of the equal sign, it has to go diagonally. If it was on the top, it's going to go diagonally to the bottom. If it was on the bottom, it's going to go diagonally to the top. So that being said, what these numbers do is they actually, we can just move them and put them way over here. Okay, so now we have 4 moles and we have 0.0821. And let's see if we can clean this up a little bit. Which leaves T, I'm gonna put T in blue, temperature, and remember, it's going to be in kelvins, okay? So we have temperature that's in kelvins, and multiply the tops, divide by the bottoms, and you should get 204 kelvins. What happens if I wanted to throw you a curveball and I said, what's the temperature in Celsius? Well, if 0 degrees Celsius is always 273 Kelvin, remember Kelvin is always 273 degrees higher. Remember, our Celsius is always going to be a number that's 273 degrees lower. So we're going to take our Kelvin and we're going to subtract 273. So we're going to say 204 minus 273. And we are getting a negative 69 degrees Celsius. Okay. Next. All right, let's do number 2. If I have an unknown quantity of a gas at a pressure of 1.2 atmospheres, that looks important. Let me circle that, 1.2 atmospheres, and a volume of 31 liters and a temperature of 87 degrees Celsius, how many moles of the gas do I have? Remember, moles and molecules, not the same thing. A molecule is an individual, a couple of individual atoms put together. A mole is a group of atoms, just kind of like how we say dozen is a group. We can group things by dozen. Let's start putting the formula. We have a formula. It is abbreviated affectionately called PIVNERT. So we have our pressure on the left, 1.2 atmospheres, and you better be putting your units down, a volume of 31 liters. How many moles are there? I'm going to put N in blue because that's what we're looking for. Let's go back to red. R. Now R, we're going to be using the atmosphere R, so it's going to be 0.0821, put that in brackets. Oops. And then we have our temperature. And our temperature is 87 degrees. Wait a second. They gave it in Celsius. We can't put Celsius in the temperature. We can't be using the unit for Celsius. We have to use Kelvin. All right, let me get the eraser out. Hopefully you can beat me. Well, if we know that 0 degrees, oops. If we know that 0 degrees C equals 273, and we have 87, that means we've increased on the left-hand side by 87. Therefore, we've got to increase on the right-hand side by 87. So let's do 273 plus 87, 360. So we have 360 K for Kelvin. All right, do some quick erasing. Now, I have numbers on the right-hand side of the equation I need to get rid of because I'm trying to single out the number of moles, N. And if it's across an equal sign, we're going to cross multiply. And essentially what we're doing is we can shift things diagonally. And that's it. We can shift them diagonally this way, or we're going to shift them this way. So what we're going to do is we're going to send both of those downtown diagonally. So we have 0.821 and 360 Kelvin. Let's see if I can erase, oops. Everything on the right-hand side. Voila. Now we have numbers on the top of the fraction. We have numbers on the bottom. Multiply the tops. Divide by the bottoms. Survey says we should have the number of moles equaling 1.26 moles. All right, this is what it should look like when you're solving these in your chemistry notebook that you're going to take a picture of and post. Okay, so you have everything there.